Okay, this is all stuff that's this review of factoring. It's all going to be stuff that you've seen in Algebra 1, so it should feel mostly like review. But we're going to go a little further with it than you did in Algebra 1. In Algebra 2, we do some little more complicated applications of this stuff. Okay, so let's start off. Let's talk about, and if you want to follow along with your packets, this is the Unit 4 packet, the one on solving quadratic equations. Okay, you don't have to. It's up to you. I'm going to continue to put the notes up, the PDFs of the notes. Every day I'll put those up on the Google Classroom, so they'll be there, right? If you prefer to use those and you don't want to go through this, that's fine. Totally up to you. Whatever works best for you. Let's take a look at this, though. We're going to start off, we're just going to talk about solutions to a quadratic equation. It says solutions to a quadratic equation are the points at which the function intersects the, come on now, x-axis. What do we mean by that? The solutions to a quadratic equation. So I want to just add one little piece to this that doesn't show up on the notes. Okay, whatever they did, they upgraded my board and it doesn't even hardly work anymore. I can't even hardly write on the thing. So I'm going to type as much as I can because the writing just is not working. Oops. Backwards. There we go. Well, a quadratic equation in standard form would look like what? You guys are used to seeing quadratic functions in standard form, and that's pretty familiar, right? That would be f of x equals ax squared plus bx plus c, right? That's a quadratic function in standard form from last unit, okay? To make this into a quadratic equation in standard form, we just set the whole thing equal to 0. Okay? So a, b, and c are numbers, and it's equal to 0. So any equation that could be written in that form, if I were to do a little algebra and move terms around, if I could write it in that form, then it's a quadratic equation. What's different between, how's that different from the functions or the equations we worked with at the start of the year? Well, those were linear equations. They just didn't have x squared terms, right? So now we're pushing this one step further and we're adding that x squared term into the mix. Okay? So the solutions are going to be the places where the graph of the left side, so if I were to take this function and graph it using all the techniques that we talked about, all the techniques that we talked about last unit, right? Graphing quadratic functions. Remember, we graphed them in vertex form and in standard form, right? And I'm still wrapping up grading those tests. I will get those back to you. And if people want to do a retake, I'll give you an opportunity to do a retake after spring break as well once you get those back. And I'll give you, I'm going to try to do it if I can find time. It takes a lot of time. But I'm going to try to put video links in them like I did before hybrid, okay? Because I think was that useful to you guys to have that where you got the comments back and you're able to click on the links and see? Okay, good. I'll really try my best to keep doing that. So if we were to graph this function, the solutions to the quadratic equation would just be where it crosses the x-axis, right? And so then the solutions, we have a bunch of different names for that. We could call them solutions. We could call them x-intercepts, obviously, if it's where the graph is crossing the x-axis. We could also sometimes refer to these as zeros or roots. Why do we use so many words to mean the same thing? Each of these implies something slightly different, but I don't want to get into the differences now. It's really not important. For now, all those are just interchangeable ways of saying the same thing. So what would a graph look like then of a quadratic equation with two solutions? How would I draw? We know that if we graph a quadratic function, it's a parabola. How could I draw a parabola that has two solutions, that has two x-intercepts? What would that look like? What do you think? A parabola with two x-intercepts. Let's say, for example, that I put the vertex of my parabola down here. Would the parabola have to open up or down to have two solutions? Have to go up, wouldn't it? Okay, so we could have an example of something like this, like a parabola that opens up with a vertex that's below the x-axis, right? That would give me x-intercepts there and there, right? We'd agree that would be a case where we get two solutions. What about one solution? How could I have a parabola that only has one x-intercept? Oh, okay, so the vertex is sitting on the x-axis. Good. And then that parabola could either open up or down, right? So let's make this one open down. How about? This board, I tell you what, it just is hardly even working. So something like that, where it's only got a single x-intercept. And then one with no real solutions would just be an example of one that never crosses the, never crosses the x-axis. So maybe something like this. This is so frustrating. I don't know what happened to this thing, but it worked fine before break, relatively fine, and now it doesn't work. Something like that maybe, okay? So what's nice about this then, that when we draw this, this parallel between the number of solutions and what the graphs looks like, well, what the graphs would look like of the parabolas, is it points out a really important relationship. We can always use a graphing utility to find the x-intercepts or the real solutions of an equation, right? For example, what about one like this? What if we were asked to find all the real zeros of this function? Well, what does that mean? Real zeros. Those are just the places where the function is equal to 0, right? So I'd take this entire function just set it equal to 0, right? Well, how could I do that graphically? I just am going to graph this parabola, f of x equals negative 1/2 x squared plus 3, and just find the x-intercepts on the graph. That's easy to do with a graphing calculator or with Desmos. I could just ask for the locations of those points, and it tells me. So rounded to the nearest tenth, the solutions would be negative 2.4 and positive 2.4. Everybody see that? Okay, that's a really easy way graphically to find solutions. Okay, so we got to learn how to do this though algebraically without a graphing utility. So let's take this example for today. This is probably about, this will probably be the only example we really get through for today, and that's okay. Some suggestions. How do you think we could solve this thing? We got an equation up there, x squared equals 13x. So my goal is I want to find all the values of x that satisfy that equation, that make it true. What are some strategies? You don't have to be correct either. What are some things you could think about doing here to solve this? I mean, we could guess and check, and we might even get the answers this time, but it's going to be pretty hard to do. There are going to be some situations where guess and check is probably going to fail us, but it is an option. What about algebraically? Can you think of a step here that might be a good idea? Wait. Say it again. you multiply, well, I can't just multiply the 13 by 2. I could multiply both sides by 2. So I'd end up with 2x squared equals 26x. Remember, I got to treat both sides equally, don't I? But that's not going to get me anywhere. Any suggestions? I could divide by 13. I'd get x squared over 13 equals x. Again, it's not really getting me anywhere. Okay, now we're starting to think in terms of, are there some greatest common factors? Well, we're moving in the right direction. We're moving in the right direction, but before we do that, what do we want to maybe do? Something doesn't look right about that. What about that 13x? Anything we could do to that? How about, what if we set it equal to 0? What if we subtracted the 13x from both sides? Okay, that sounds like a pretty good option, okay? So one possibility, we'll call this is our first strategy here. Would be to subtract the 13x to one side, and so it's all equal to 0. Okay, good. Is there anything else you could think of? I'll tell you what, sometimes what people suggest here, sometimes, and this is not correct, this isn't going to work, but sometimes people suggest we could divide each side by x. Everybody see that might be something that person would suggest. If I started off, so I'm going to divide this up. So we got strategy 1, and now over here we've got strategy 2. What if we I divided each side through by x? Oh my gosh, this stupid thing. So that's going to cancel an x here, right? So I end up with x equals, x's would cancel there. I just get x equals 13, right? Everybody agree? Well, how could I check to see if that solution's correct? How do I always check to see if I got the right answer? I mean, I could undo it, right? How could I go back to my original equation and just see if it worked? Yeah, I could plug 13 into my original equation and see if it makes the equation true, couldn't I? So I go up to my original equation and I plug in 13 for x. That's going to give me 13 squared This is driving me nuts. I mean, this thing is like just about unusable now. That would give me 13 squared equals 13 times 13. Everybody agree if I plug in 13 for x? That's true, isn't it? 13 squared equals 13 times 13. Well, that seemed pretty easy. What's the problem, though? Can anybody see any other solutions? By guess and check, can you see any other solutions that would have worked that I could have plugged in for x to make this a true statement? There's one other number that would have worked that we didn't get. Think about a really easy number. Well, we could try negative 13, but if I square negative 13, I'd get positive 169 equals 13 times negative 13. Well, I'm going to get negative on one side and positive on the other. So negative 13 is not a solution. But there's another one. Think about the simplest number you can think of. Well, maybe not maybe the second simplest. 0 would work, wouldn't it? Right? 0 squared would equal 13 times 0, wouldn't it? Okay, so we lost a solution here. So turns out that this is not something we can do. That strategy 2 is a bust. It doesn't work. It's not something we want to do. Here's why. I'm going to type this because I'll never be able to write it up here. Because when solving an equation, never divide both sides by a variable. Because you lose solutions. Which we did, right? We lost the 0. Didn't work, okay? So that's not a strategy that we want to use. Okay, this strategy was a good one though, okay? Let's go a little further with this. Let's do just a little quickly, let's do a little post-spring break warm-up here. Just a little mental math to kind of warm things up a little bit. Okay, so we're just going to do some multiplication. So 2 times 3, everybody's got an answer, right? Take that answer and let's go ahead and multiply again by 5. Got a new answer in your head. Go ahead and multiply by 3.14159. Okay, now hurry. Come on, you got this. Hurry. Okay, I guess that's probably enough time. Now multiply that one by 78,901,512.132. Okay, you got this. Kelly, you got this, right? No problem. Multiply by 77.901. Everybody should be fine. Multiply by 0. And let's see how good you were. Everybody get the right answer? What's the answer? Oh, see, look, you could deal with those big numbers. No big deal. You get 0. No biggie. I had faith in you. I knew you were going to get this. So what's the moral of the story, right? Well, what's the only way I can multiply numbers together and get 0? Only way I can do it is to multiply by 0. If I have a string of numbers that multiply to 0, right, then the only way that they can equal 0 is if one or more of those numbers were 0. I can never, ever multiply non-zero numbers and get 0 for an answer, okay? So this pretty simple idea is a big deal in math. It's what we call the zero product property, okay? Zero product property in its simplest form just says that if we have real numbers A and B, if A times B equals 0, then either A has to be 0 or B has to be 0, or maybe both, okay? And we could extend that to even a longer list of numbers if we want to. If we take all the real numbers, A, B, C, et cetera, dot, 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 for as many numbers as we want, and then the last one we'll call omega. It's just a Greek letter. If the product of that big string of numbers is equal to 0, then what has to be true? Either A is 0, or B is 0, or C is 0, et cetera, all the way to the last number in the chain. One of those has to be 0 at least, right? So how can we use that to our advantage here? Well, you guys took the correct first step. The correct first step was to set this thing equal to 0. The zero product property only works if we set everything equal to 0. So we had to subtract the 13x over to this side. Okay, but it's really difficult for us to come up with the numbers that are going to equal 0 when we're adding or subtracting terms. That's darn near impossible in most cases. If there was a way for us, though, to break this thing apart into a product of factors instead of a sum of terms. Terms are things that are added or subtracted in math. Factors are things that are multiplied. So if we were able to break this apart into a product of factors that equals 0, we could use our zero product property to get the answers. okay? The process of factoring, what does that mean? So factoring means that we're taking a polynomial, which in math is just a sum of terms, and we're going to break that apart into a product of factors. That's relatively hard to do. That's what we're going to review and spend some time on. The reverse of that process is we start with a product of factors and we turn it into a polynomial, a sum of terms. That's easy. That's just multiplying, right? In this case, if I told you to simplify this, you would all tell me, well, just distribute the 3x, right? And if I distribute the 3x, I would just get this. That product of distributing or multiplying in math is what we call expanding. That's our general term for going the opposite direction of factoring. Okay, but let's see if we can do this. I know it's been a while, and we're going to talk about this today, but does anybody have an idea how I could factor that expression on the left side? Could I break it into a product? Yeah, what do you think? Okay, so you're undistributing an x, aren't you? Right? You're factoring out an x. If I undistribute an x from both terms, what's left behind? X times what would give me my x squared if I distributed it? Okay, everybody see that? X times what would give me my negative 13x? Okay, so we just reverse the process of distribution, right? That's what we call factoring. We give a name to this x. The biggest thing that we're able to undistribute is what we call the greatest common factor. Right? And what we're left with is what we get when we undistribute the greatest common factor. Okay, another way to think about that would just be to divide. If I want to know what goes there, I could take the original term and divide by my greatest common factor of x. Well, what's x squared divided by x? It's just x, isn't it? Same thing over here. I could take my negative 13x that I started with and divide by x. Negative 13x divided by x is my negative 13. Everybody see that? Okay, and now look, I've got this thing broken apart into a product of factors. So look what this does for me. That may not seem like much, but that's huge. So if I have x times the quantity x minus 13 equals 0, well, by the zero product property, the only way that that factor times that factor can equal 0 is if one of two things is going on. Either the first factor, x, has to equal 0, or the second factor, x minus 13, has to equal 0. So one solution is x equals 0. What value of x is going to make x minus 13 equal 0? 13, right? I just add the 13 to the other side. There are my two solutions, right? By applying the zero product property. Everybody see that? So if I can set the equation equal to 0, factor the left side, I can use the zero product property to get my solutions, okay? All right, well, what happens, and here's where we'll end up for today, I think. Come on. Okay, what about this one? Actually, we got a couple other quick examples. What about that one? You guys could probably factor that one for me. Look at that one. Is there anything I could undistribute there? What do you think? Anything I could undistribute? Yeah, okay, good. I could factor out a 3, couldn't I? Right? So if I want to factor this polynomial, There's my greatest common factor right there. Oh, this is so frustrating. I don't know what I'm supposed to do to make this thing work. Nothing seems to work. So my greatest common factor is 3. If I undistribute that, what's left behind? Okay, good. So 2x cubed. If I divide 6x cubed by 3, I get 2x cubed plus, oh my God. I don't know, I'm about ready to just junk this whole thing. 9 divided by 3 is 3, right? And that whole thing is equal to 0, right? And so now I could just set those two factors equal to 0 and solve if I wanted to, but it didn't tell me to do that last part. All it told me to do was factor it. Okay, and so it's factored, that's it. Okay, what's the moral of the story? Well, even when we get into more complicated factoring problems here real soon, the first step we're always going to try to accomplish is to factor out the greatest common factor, the GCF. It always is our first step. There won't always be one, but we're always going to try. Okay. All right, here's the last example. So what about one like this? Here we've got a little bigger polynomial. It's got bigger powers of instead of x, this time a is our variable. Notice that each term has both variables and numbers associated with it, right? So when I'm factoring out the greatest common factor, there might be a number part of it and a variable part of it, okay? Well, let's start with the variable part because that's actually the easiest part. So my GCF then, what's going to be the variable part of my GCF here? What's the biggest power of A that I could undistribute from that expression? It's either going to be probably 4 or 2, isn't it? I can't take an a to the 4th away because that one's only got 2 to give. Think what an a squared is. That's just an a times an a, right? What's an a to the 4th? That's a times a times a times a. Well, this one's only got a string of 2 a's, so it can't give away an a to the 4th. So the GCF is always going to be, the variable part is always going to be the wimpiest or the smallest power of the variable. Right? So it's going to be an a squared. So that's the variable part of it. Okay, now what about we still have, what's the other stuff though? What's left behind from the other terms? Well, if I take an a squared out of the first term, a squared times what is a to the 4th? A squared times a to what power would be a to the 4th? Let's review this rule of exponents real quick. So if I have a to the m times a to the n, what happens if I multiply like bases like that? What do I do to the exponents? I add them, good, right? It's equal to a to the m plus n. So for example, a cubed times a squared is a to what power? Anybody agree with the 5th? 3 plus 2, okay. So then up here, we should have a squared times, we'd have an a squared, wouldn't we, in our first term? What about the second one? We're going to get another term in there, a squared times what is a cubed, so we're going to get an a left over in our second term, and then a squared times what is a squared? Well, that's just 1, isn't it? Right, so there's not going to be a variable in my third term of what's left over. What about the numbers? What's the biggest number that divides into 8, 16, and 4? Be 4, wouldn't it? Okay, so we know the number part is going to be a 4, But the question everybody's going to have is, what about that minus sign, right? Okay. What about the minus sign? If I write this polynomial in the correct simplified form, we always start with the biggest power of the variable and work our way down. So in this case, a to the fourth is the biggest power of a. We call that the leading term. Because it has the biggest power of the variable. The rule is the greatest common factor always inherits the sign of the leading term. So because the leading term is negative, we're going to undistribute a negative 4a squared. So then negative 4 times what is negative 8? Everybody agree that's a positive 2? Okay, so we get a 2a squared. 16 divided by negative 4 is negative 4. So our middle term is a negative 4a. And then negative 4 divided by negative 4 is 1. So we got it. Make sense? Okay, good. All right, that's a great place to stop. All right, everybody grab one of those, what are those little wipies there? What do you call those things? I don't know. What is it? Yeah, there's actually the one right there. Just use those ones on that yellow thing on the desk there, the little Clorox wipes. Grab one of those and wipe off your desk and just toss it in the garbage on your way out. Have a great day. I will see you virtually on Wednesday morning, right?